In this next part of the electron configuration discussion, we're going to talk about some more in terms of what happens when electrons come or go from an element, and then how do we start to use this idea of where electrons are and how these compounds start to come together. So first I wanted to start with a conversation about transition metals. These are not as easy to predict which ions are going to form. You'll have to look a little bit more at some stability factors that come into play. So, for example, let's look at, if we look at exactly filled or half-filled subshells, these tend to be extra stable. Let me show you why that might be. So if we have a d orbital, we know that we have 5 different orientations of that d shape. And these 5 orientations, if we have 5 electrons, they can be split up into these 5 different orbitals. Now you'll notice that when we have 5, there's 1 electron with the same spin state in each of these orbitals. So manganese might tend to like to have a +2 charge. Now does this make sense? Are they going to lose these 2 electrons? Actually, remember what we're kind of forgetting, or what's not being shown here right now, is this is the electron energy diagram for the +2 charge state. We have removed the 4s2 valence shell electrons. These are the 2 that are going to leave to give us a positive charge. Remember, electrons are negatively charged, so if that goes away, then we get a +2. And these are stable because we have 1 electron in each of these orientations, these d orbitals. I like to think of them as little rooms. Zinc is another one that likes to have the +2 because we've also that 4s2 orbital. These are going to leave, and that is going to give us a +2 charge. And here we have 1, 2, 3, 4, 5 orbitals, and we have 10 of these. So we have an up, 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 up. There's 5. And then we have the opposite electrons in the other orientation. So that gives us 10. These provide extra stability. Anytime then we can have something where we might have, again, 5 of these, and maybe we have 1 or 2, these extra ones might also leave. Or if we have, for example, 6 electrons, right, these other ones might leave, be more easy to leave. That'll be another type of charge state that a transition metal might have. So they're always trying to tend towards the completely filled or the half filled, where there's 1 electron in each orbital rather than 2. So the next question, if we are going to consider bismuth here, let's look on the periodic table quick. It's all the way down here in 83. So we're going to be coming from the d orbitals. We're going to get into the p orbitals. Remember, the s and p orbitals are going to be our valence electrons. And we want to, it's nice to rewrite that, showing you where those valence electrons are. Those are generally going to be the first electrons to be lost, and with the largest n value, or the principal quantum number, which is that 6 here. And we can come from the highest subshell, but what we see is we typically will get a bismuth +3 or a +5, because we could lose these 3 first. That would give us the +3. And if we also lose the other 2, that will give us the +5. So these will be typically where we would find the electrons leaving. Now these are full. The d orbital's filled, so we wouldn't likely mess around with that. Again, the half full or the completely full d orbitals are going to be stable. Now I want you to try this with iron. So here is the noble gas configuration, the lowest energy diagram configuration, electron configuration for iron. What are the ions that might be expected based on this energy diagram or electron diagram? I'd like you to pause and try this out. before you continue, I'm going to now just kind of give you some hints if you are stuck. The first thing to do is remember what are the valence electrons. What are the electrons on the outside? And in order to determine that, we have to look at that principal quantum number. So 4, that's the largest shell. And these are the first ones that might be lost. So one option is going to be Fe plus 2, because these electrons are going to leave and it'll give it a plus 2 charge. Now we could start to go into this d orbital where we have a d plus 6. Remember, we have 1, 2, 3, 4, 5 different orientations for the d orbital. The s orbital just has 1, the p orbital has 3, the d orbital has 5, f orbital has 7. The d orbital, in this case, we're going to have 1, 2, 3, 4, 5, 6. So one of those electrons is going to have to double up. And remember, we said half or completely full orbitals are going to be the most stable. So if this one leaves, we then will have something that is equal to, we have 1, 2, 3, 4, 5. We'll have 1, 2, 3, 4, 5 electrons. But then we'd lost one additional electron. So that would give us a plus 3 charge now, where the new charged electron orbital configuration would be 3d5, and the 4 s2 electrons are now gone. This would be the next most stable form. So this would be for the iron plus 3. The iron plus 2 would be argon 3d6. So these are two of where the electrons would be located for a plus 2 or a plus 3 iron, which are the most common different types of forms of iron. So we were looking previously at metals, now looking at nonmetals. Remember, these are going to want to gain electrons. They ultimately want to become isoelectronic, or similar in how their electrons are organized with the next largest noble gas. These have a higher electron affinity, which means they want to pull electrons towards themselves. Now here's an oxygen, and we have the 2s orbital is filled with 2 electrons, and we'll have 1 and 2 in the 2s orbital. And we also have the 2p orbital, 2p, that's going to, remember, have 3 orientations. We have 1, 2, 3, 4. So we basically have 2 spots that are open for oxygen, which means there are 2 available beds in these 2 rooms. That's the analogy I like to use for electrons to come in. So here we can actually add 2 electrons here, right? And then we will get an oxygen with a -2 charge, or a 2 minus charge. The electron configuration for that charged oxygen is going to be 2s2, 2p6, right? 2p4, we add 2 electrons, and that's going to give us 2p6. We've added those 2 electrons. Now try this with the nitrogen. I'll give you just a moment to look at this, look at how these compare with oxygen, and then make a prediction on what you think that charge would be and what that final electron configuration is going to be. And you can pretty well see here, if we do the same thing, we're looking at, right, the 2s is filled. We don't need to worry about that. It's the 2p orbital. We have 1, 2, 3. So we have 3 spots here that are empty where electrons could go in. We could add 3 electrons here, which would give us a -3 charge, and that would give us the same exact noble gas configuration here. So this is going to be what we're ultimately wanting to do, is get this to the next biggest noble gas configuration. Now I'd like you to look at and try this out with the electron configurations for zirconium-2 and zirconium-4. Remember, when we talk about metals, and if they have numbers, Roman numeral numbers behind them, that gives us a hint as to the charge state of those metals. So use this to write out the electron configuration based on that. Remember, if it's a positive 2 charge or a positive 4 charge, that means it lost that number of electrons. So take some time to do this, post your answers in the Blackboard space, and then we'll move on to the next step here. Now that we have a little bit of experience with electron configuration and what those things mean and where electrons are found, now I want to introduce you to this new idea called Lewis symbols, or the Lewis structures. And this is really a bookkeeping method, an accounting method for the valence shell electrons. So the electrons in the largest principal quantum number shell. We write the chemical symbol, and then we surround that with the number of dots next to the symbol associated with the different electrons. So for example, if we're looking at hydrogen, lithium, sodium in that first column of the periodic table, each of these has one electron in that valence shell, in that S shell. So it's NS1, that would be the number of electrons. For the next column, we have helium, beryllium, magnesium, calcium, for example. These would have 2 electrons in their valence shells. We can move over on the periodic table. These are the tall rows. For reference, they don't include the transition elements. We don't use Lewis symbol for the transition elements because of what we were just talking about before, where those tend to like to be half or completely filled. It gets more complicated than this. Lewis symbols are really good for organic compounds and generally biological compounds that utilize some of these elements with the longer, taller rows that don't include the transition metals. So that first row in the 3A, the boron, we have 3 electrons in that valence shell. We have the 2 from the s orbital and then 1 from p. Aluminum is also that same way. If we go into the next column, we have calcium and silicon. Those are going to have the 2s, 2p organization. So each of these has 4 electrons in their valence shell. Now we're going to go into the 5A next. And we can see we have nitrogen and phosphorus. They'll have the 2 in the s orbital and then 3 in the p orbital. So they'll have complete 5. And then we go to the 6A with oxygen and sulfur. They'll have 6 valence shell electrons, and then fluorine, chlorine, and then finally the noble gases. And we brought helium over here as well. Obviously those don't have p orbitals. They're in the top row. They only have the s orbitals available to them. So this is a way that we can look at the electrons and how many might want to come in. For example, all of these 5A, 6A, 7A, we have spots available for electrons. And we typically do this on 4 different sides. So we have 1, 2, 3, 4, 5, 6, 7, 8. So those 4 sides, those represent different spots where electrons can go into. So here we can also look at using this to start to kind of examine and look at chemical reactions. In organic chemistry, when we have arrows here, these arrows actually mean specific things. So we always draw arrows from electrons to where they are going to go. This seems to be confusing for a lot of people doing this, but this is the standard use for the arrows within chemistry, looking at electrons being at the base, and then the arrow points at where they are going to go. Notice this is 1 electron, and it's actually a one-sided arrow. It just means that it's just moving 1 electron. If you have 2 arrows, or a 2-sided arrow, you're moving actually 2 electrons. So we can use the dot structure to show this transfer from sodium to chlorine, or now a chloride ion. So the sodium is going to be a positive charge because it lost that electron. And you can see here that blank spot now has that electron and it becomes negatively charged. We can do this with other elements. We have magnesium is losing 2 electrons, oxygen gaining 2. So this Lewis structure helps us to organize and account for electrons. We can't gain or lose electrons from an equation. So it's just like balancing it's just like balancing an element in the periodic table. You can't have just the creation of a water from nowhere. It has to come from somewhere. The same with electrons. Those are matter, and you can't just create those out of thin air. They have to come from somewhere. So this is just our accounting system to make sure that we know where the things are. And notice the charge here, a +2, a -2. The overall charge on this side of the arrow is a 0. The overall charge on this side of the arrow is also a 0. So we have a 0 charge, and then a plus and a minus. That's also a 0 charge. So charges, remember, those have to be balanced, and really it's talking about balancing electrons. This Lewis dot structure idea starts to introduce us to this idea now of covalent compounds, because the Lewis structure is showing us, remember, the valence electrons, and those are the electrons that are outside, the furthest away from the nucleus, the most available and able to interact with the surrounding, the outside environment. These are the spaces where atoms start to be shared, and they can be involved in being shared by other atoms. And this is called, when that sharing happens, called a covalent bond. So let's look at this process in action here using this Lewis dot structure idea. If we have hydrogen gas, we have a hydrogen with one electron, hydrogen with another electron. Remember, hydrogens have one proton. They would have one electron. This is the most simple covalent bond, where we have, but in an s orbital, we have room for 2 electrons. So they have space in their orbitals. They each have space. And now we have 2 electrons here. We have 2 protons. So they have fused together. They have created a new bond that would release energy from this starting point, right? So we have a lower potential energy. They've come together, and now we can also write this out as these sharing electrons here. We can write it out as a single line. So that is the same kind of idea. If we have a line, it means there are 2 electrons being shared between that bond. Another example is fluorine. So if we have a fluorine compound, 1, 2, 3, 4, 5, 6, 7, like I showed you in that last chart, looking at the various elements, fluorine is going to have, and all of the elements in that column are going to have 7 valence shell electrons. They can use this open spot here in each of their orbitals to allow for bonding. And this is equivalent to, right, these 2 electrons are being shared. This line means that those 2 electrons are being shared. And this is going to form a single covalent bond. These electrons now on the outside, these are called lone pairs of electrons. So we have 1 lone pair, 2 lone pairs, 3 lone pairs per fluorine compound here. So 3 on each. And those we're going to want to keep track of, because we're going to have some interesting things that we use with those later on in the semester. This is the same exact structure that you're going to see for chlorine, bromine, iodine. If you're just basically replacing the F here with the Cl, Br, or I. But because they're in the same column on the periodic table, they're going to have that same Lewis structure for the diatomic gases. We can also have diatomic gases which are multiple or different types of compounds. So hydrogen and fluorine, for example, we have 1 electron in hydrogen, we have 7 in fluorine. They both have a spot here for bonding, and we can put these together, and this line again represents those 2 shared electrons. HCl, HBr, HI, this is the same concept and the same things that are going to happen. Next, I want you to think about how many electrons are required to complete the octet around nitrogen. So the hint here is to determine the valence electrons. What's the starting point? How many do they have? And how many more do we need to get to that octet? Remember, octet is 8, and that is filling up the s orbital, which would be 2, and the p orbital, which can hold 6. So 6 plus 2 is 8. That's where that octet rule comes into play. Determine this, post your answer in our Blackboard space, and then I'll move to the next step. So we just went over a few simple Lewis structures for very simple compounds. I want to show you, still fairly simple, but kind of moving up in complexity here. Methane gas. This is an element that contains carbon, which has 4 valence electrons. And as you have maybe guessed, if we want to get to 8, we need to add 4 more electrons somehow. So one of the ways to do that is by loading that up with hydrogen elements, which each are going to provide 1 electron each. So these are 2 different ways. Here's the Lewis structure, dot structure. This would be a traditional method for showing you these single bonds that are sharing 2 electrons in each bond here. This is methane gas. This is the structural formula for methane gas. Nitrogen, you'll notice it has a lone pair of electrons. So these are paired up already, but they have spots for 3 more electrons. So we can do the same thing. We can load it up with hydrogens, and you've guessed it, we need 1, 2, 3 hydrogens here. And these are going to show you those shared electrons with those lines, and then the lone pair on top. We're going to do now look at oxygen. These have 2 lone pairs, 2 open spots here, and we're going to add 2 hydrogens. This is the formula for water. You'll see it's sharing 2 pairs of electrons, the oxygen and the hydrogen, and the oxygen and the hydrogen. And the oxygen also has 2 lone pairs of electrons. This is really important for the shape of this compound, and we'll talk about shape in the next chapter. Those previous examples were showing you single bonds, like the methane gas. We have 1 pair of electrons being shared. We can get more complicated where we actually share more than 1 pair of electrons, and that is going to be kind of demonstrated here. If we have oxygen with these 6 valence electrons, and carbon with 4, the starting point, we can actually share these 2 oxygen electrons with these 2 spots in carbon, and these 2 unshared, unpaired electrons with carbon. So we're going to donate all of these, and we're left with something that looks like a Lewis structure of this, where we actually have 1, 2, 3, 4 being shared between this oxygen on the left and the carbon, and then 4 more with the carbon in the center and the oxygen on the right. This is equivalent. Now we draw these 2 lines. 1 line is equal to 2 electrons, so 2 lines is equivalent to 4 electrons. 4 electrons are being shared on the left side, 4 electrons being shared on the right side. This is carbon dioxide. This is how this looks, and this is the Lewis dot structure for carbon dioxide. Finally, we do have triple bonds as well. This is the last type, and we'll talk about this later when we talk more about the symmetry and the orientation, the geometry of these things. But we can share 3 sets of electrons, or 3 pairs of electrons, and this will give us a triple bond, which we have 2, 4, 6, right? Each one of these represents 2 electrons being shared, and so this would represent 2, 4, 6 electrons being shared, also shown in the middle here in the same way. But this is typically how nitrogen gas is going to be shown as in a Lewis structure. All right, so now I want you to look below, and here I want you to look at what species is most likely to have multiple bonds. In order to do this, you're going to want to just kind of how to figure this out. First of all, you want to look at the number of valence electrons that these compounds are going to have. Usually you want to look at that thing that's going to have the least number of valence electrons and likely to have to add the most number of electrons to give it an octet. Everything you're going to want to have an octet. Never use hydrogen as that molecule though. Hydrogen's always kind of the filler. It fills in those gaps where electrons are needed. So for example, look at the difference between carbon and oxygen. How are you going to connect these and give them both an octet? Oxygen, we kind of looked at water before, so likely probably not that one. This phosphate, the boron, the carbon. You want to focus on these elements here and how do these other elements fit around to provide that, to determine if one or the other is going to have multiple bonds. Post your answer in Blackboard and we'll discuss this. Now that you've been introduced to Lewis dot structures and covalent bonds, I want to look a little more closely at what's happening with the electrons in those covalent bonds. And this is a diagram below looking at kind of a scatter plot, the probability kind of going back to those probabilities of a sphere, the s orbital, where the electrons are going to be found. And when these come together and bind, they're actually still, these electrons are going to be found anywhere in here. So they have the single orbital. They're going to have probability of being in here in any spot at any one time. And the distance between the nuclei, you can see these dark black orbs here are representing the protons. Those come together and they're going to be a lot closer in distance than they were as individual atoms. So these nuclei pull closer together and they kind of pull these and tether these nuclei together in this form. In a covalent bond, there are really two different things that we're looking at to determine the energies involved and the strength of those. So we're looking at the bond length, and that's the difference, the distance between the two nuclei of the two different proton groups. And this is going to tell us something about that bond character here. The other thing we look at is bond energy. Remember, when a bond forms and these two protons, for example, come together, there is going to be energy released because this releases energy as these electrons come closer to more positive charge. If we want to break this bond and pull the electrons away from those other protons, then that's going to require energy. Bond length is one characteristic, and the amount of energy that's associated with that bond is another. There's an interesting characteristic with that bond length and energy as well, because as we start to push those protons together, they start to repel each other. So there's only a certain distance that we can get those, and as we start to push those closer and closer, so here's a graph of the distance of separation, so really far apart would be on the right, really close together would be on the left side of the x-axis, and when we're going from low energy on the bottom here up to high energy, this state with this red line, this is telling us this is the lowest energy state when they're 75 picometers apart, for example. If we start to rip them apart, then this requires some amount of energy to pull those electrons away from the other proton. But if we start to push them together too close, then the energy starts to increase because the protons start to repel each other in the two different nuclei. So there's only that you can only get them so close. And then this energy rises a lot because we'd have to push them. We require a lot of energy to fuse these together, to push those protons together into one group that would then essentially create a new element. If we, for example, push two protons together, then that would be helium, for example, instead of hydrogen. Here I want you to look at this question determining what is the primary driving force behind the formation of covalent bonds. One of these answers is correct. I want you to indicate which answer you feel is correct and why, or why the other ones are not correct in your answer that you post in Blackboard. Here's a kind of similar type of question. What forces limit the distance between the nuclei in a covalent bond? And here are 5 different options. I'd like you to tell me which one is the correct one and why it's correct by either describing why the answer you gave is correct or why the other 4 are incorrect. In the next section, we're going to start talking about electronegativity in these types of bonds and bond polarity, essentially where we're looking at two different nuclei. So here, if we have the same nucleus with it's a proton, a single proton in each one, those electrons are going to be found here in this space pretty much evenly around one versus the other. But when we have different shielding, or we have different amounts of protons in one side versus the other, like when we're sharing electrons with hydrogen versus chlorine, there's going to be a change, a difference in where we find the majority of electrons. And where these electrons, even if it was from originally the hydrogen, where that electron is found, it's going to be a higher probability it's going to be over here by the chlorine than it's going to be over here by the hydrogen. And we're going to talk about that in the next section.